All right, recording is rolling. It is Tuesday, May 21st. We're on this fun schedule. We're doing period 7 exams today. So today's the last day you'll be in your period 7 class. Right? Classes here. And then, guys, laptops, you guys are turned in this week. I had some students already turn their laptops into me. So if you guys find a good time, if you want to check it in, I'll be able to do that. Right? Maybe you want to get your files off, maybe want an extra couple days to have it to study for some things, but yeah, sometime pretty soon we turn that in. All right. So you guys ready for FRQ solutions? FRQ? All right, so here you go. Here's FRQs. First one, right off the bat, that looks not exactly the same, but extremely similar to this poster. You guys remember this poster? Right? There are two main ideas embedded in this poster. So one idea is that there needs to be some, okay, so you got this roller coaster going around this vertical loop, right? There needs to be some speed to get around. The minimum speed is square root GR, right? That's it. Right? And then the idea you can connect to that is you can backtrack and say, okay, well, what height do you drop it from? So that can happen, right? Right. And then I got the solution here. Right, so there's like unit 3 circular motion, and there's like unit 4 conservation of energy effects, right? Right. So they got one that's reminiscent of that. Right, so roller coaster, loop radius R, another loop radius R and height. Okay, lift it off the ground a little bit. The initial drop height was 6R, and they also mentioned frictional forces are negligible. Okay? And that's a key detail because energy would be conserved. There's no frictional. Right. So you guys go with the setup the premise. All right. Off the bat, first question. Energy charts. So we've got an energy bar chart represents gravitational potential energy and kinetic energy for the block Earth system. Okay? At point A and then at point B, point A and point B. So go back here. Here's point A. Here's point B. Right. So we're going to draw on these charts. All right. Now, conveniently, look, it's 1, 2, 3, 4, 5, 6 units tall. Now, energy could take the form mgh or 1/2 mv squared. Right? And okay, actually, I guess the shaded bar would be mgh, wouldn't it? Right? And oh, look at that. This is 6R units high, and this is 6 units tall. Hey, every single one of these units could sort of represent a radial height distance, right? I know it's mgh. So, guys, for diagram B, what did you guys draw at point B? How many units tall is potential energy? 2, right? And you can use mgh to exactly figure that out, right? It's like 2 radial distance high, so mgh was 6 tall, now it's 2 tall. Okay, right. mgh is proportional to, right? Well, if there's 2 units there, and there were 6 units altogether starting out, then how many are left over for kinetic? Yeah, the other 4. 1, 2, 3, 4. Right? That should be the answer right there. Right? You guys think? Right? Show hands. How many guys got that? We got that. Oh, all right. Getting some points. Okay. If you got one but not the other, it depends how they scored it, because this would be out of 7 point. I don't have the grading rubric. I don't think the grading rubric's been released at all, has it? No. All right. So I can only guess, right? This is either worth 1 or 2 points. So however they scored it, right? Hopefully they're worth 2, and yeah, let's see. Right. Use conservation of energy to actually, let's see. Well, there's a part C. So right. Conservation of energy to derive an expression for the speed of the block at point B. Express our answer in terms of R, physical constants, say gravity field. Right. Begin your derivation by writing a fundamental physics principle or equation from a reference book. Right, so, guys, what's the guiding principle? What is equal to what? Sum of energy at point A equals sum of energy at point B would probably be it. I would write that as my first line for initial final that we did. Right? Right. And what type of energy term goes for point A? Yeah.
We also find just like non-final.
To do what?
We also find energy non-energy final.
Well. Yeah, energy initial, energy final. Yeah, that should be good too. Okay. So did you guys say mgh, but instead of h, you guys put in what for point A?
6R.
Yeah, 6R, right? Because that was the height, right? And by the time you get to point B, right, so you got m times g times 2R and relative to the ground. Yeah, exactly. F squared, right? And we're solving for that v, right? Just like that, right? See, there's 3 energy terms: point, match the graphs, the whole deal, right? Guys, every single one of these terms has a what in it that you can cancel. M. So your final answer should not have anything to do with the mass of the block. And so we got 6 GR here. I got 2 GR here. Hey, can I subtract that over and make 4 GR? And then that's 1/2 V squared times 2 square root. V should be the square root of 8 GR. Or yeah, if you like, yeah, could have said 248, could have taken a 2 out and then done times root 2 GR. Yeah, good. So either one of those would have been good. Right? Don't have to do both, just pick your favorite.
I think I laid it on.
Right. Okay. Right. All right. Show hands. How many guys think you got that one? That one? Ooh. All right. All right. A bunch of hands. All right. Nice. Nice. We're doing good so far. Lots of points. Any questions so far? Guys doing all right? All right. On the following diagram, which represents the block, draw a label of forces, not components, exerted on the block at point C. Each force represents. Okay. You guys know how to draw a precise diagram. Start on the dot and draw arrow pointing away. So point C. Guys, point C is right here. Now, you know what I'm starting to wonder, because it's getting pretty far up there, is I am thinking about this in the back of my mind, right? Now, there's a couple of differences, but here. Oh, let me make a couple more, or let's do this modification. You guys see a little tiny circle with a little tiny radius r, right? What if the circle was like full sized and had radius 2r, right? So it's a big old circle. Can you guys imagine that for a moment? It was radius 2r, right? If that was the case, and you're thinking about this poster, then what would be the minimum height of the hill to guarantee that it just barely gets around?
More than.
Well, hold on. If this has, here, if there's a big old circle here, maybe I'll break out the purple ink, right? What if there was a big old loop and it went like straight into the loop like that? That's what I'm thinking, right? Guess that, right? So I got radius 2r, so that'd be like 1, 2, 3, 4, right? So 5 how's r, right? Wouldn't that be like a hill height 5r is what it would come out to be, right? 5r, right? If you dropped it from there, then it would just barely get around, right? Now, this hill is a little taller than that, 6r, right? Also, it's not a big old loop. It's actually a smaller radius circle, right? Which makes it easier to get around, right? So put those two ideas together. I think this block is definitely going to make it around. I don't think it just barely makes it around. I think it will get around, right? It'll get around, right? Now, I haven't actually calculated, I think you could calculate, I haven't actually calculated what would the normal force be compared to the weight, but I'm going to make a guess. Yeah, maybe I should have calculated. I don't know. Does anybody know the exact answer?
I did less.
Yeah, that's what I'm going to guess. I'm going to put mg is like this. I'm going to draw a normal force is a little bit less. I doubt that AP would get so specific as to where they got correct magnitude relations, but that would be my guess, maybe something like that. Okay, and you could probably calculate it, know exactly. Right. A student claims that 4r is the minimum height, point A, so the block can slide through point C without losing contact with the track and make it around. Briefly explain why that claim is incorrect. Ooh, look how nice they are, because they could have said, is it right or not? How do you check a box and then justify it? But no, they're telling you that it's not going to work. And I want you to say why. So let's go back to this. Right? So if you were, right, so point C is already up at 4r from the ground level, right? So if you sketch straight over, right, this student's saying, well, you should be able to drop a block from that point, that same height, and that'll barely make it around, right? Guys, why is that not going to work? Yeah.
Well, I did in terms of conservation of energy, and I explained it in that since both would have the same height, they would both have the exact same potential energy.
Right.
Leaving no room for energy to be converted into kinetic energy.
Right.
And it would just fall.
Yeah. Okay. Yeah, I like that track thing, right? Yeah. So all the energy at that point, C now would be back in potential. There would be none left over for kinetic, right? But you need a speed to get around. That kind of connects back to unit 3, right? So you need some minimum speed. That's kind of this idea here. In fact, if you mention Haskell, at least square root GR worth of speed, right? That maybe would have been even better, but they went that granular with the scoring, right? Yeah, you guys would have said that, right? Right? You guys like that, right? Right. Hopefully, said something pretty close to that. Okay. All right. All right. So you guys good so far? You guys doing pretty good? All right. Number 2. Ooh, this is the experimental design, a 12-pointer. So we just did a 7-pointer. This one's a 12-pointer. Okay, so you guys can see from the diagram what's going on. They just explain this here, right? But they mentioned this really important detail. the student has access only to, okay, so we got cylinders of unknown masses, okay, a stopwatch and a digital scale. I'm going to underline those. A stopwatch and a digital scale. And then a little bit later, they start filling out the table for you guys, and they also list the stopwatch and the digital scale, right? So giving you the only measuring tools you're allowed to use. And the ultimate question is, oh, what is the spring constant K? Here it is. Determine the spring constant K, right? We're supposed to find out, right? So design a procedure that another student could replicate, right? Oh, and they also mentioned this detail, reduce experimental uncertainty. So they give me a big hint right there as to what one of the points always is in this FRQ. So you guys remember that too. It's multiple trials, right? Just say multiple trials, right? Pick up that one, right? So here, I'm gonna list out some formulas I remember about springs. I remember Hooke's law, F equals Kx. I remember energy in a spring is 1/2 Kx squared. And I also remember time period for a spring to oscillate is 2 pi times the square root of m over k for this one, right? Or something like that, right? Is that true? Right. Now, this particular setup with the tools that they gave you, they're really honing in on one of these particular methods. Guys, which one of these? First, second, or third?
Third.
Third, yes, because you have a scale so you can measure masses, check, check. And you have a stopwatch, check, so you can measure the time period. So you can ultimately figure out what is K. You see that? Right. If you mentioned Hooke's law, notice they never said you had a ruler or a meter stick. Right? If you said Hooke's law, I wonder if you got the whole thing wrong, or, or I don't know, maybe pick up a point somewhere, right? But hopefully you did not say Hooke's law, okay? Right? Hopefully no Hooke's law, I hope, right? Here, quick show of hands. How many guys picked that third one and went with that third one, spring oscillation? I hope, right? All right, because I think so we're going with this. Okay. Okay, so yeah, I would say, okay, so put on the different cylinders one at a time, let it hang to the equilibrium point, then pull it an additional amount, maybe like 1 centimeter. It doesn't matter how much you stretch it because amplitude is not part of this equation, right? And then time it like, you could time 1 oscillation, you could time 10 oscillations and divide by 10, right? You do that, right? You want to definitely mention, again, of course, multiple trials per cylinder, right? Of course, measure the mass of cylinders, right? Okay, so there's a quick rundown of probably the points they were looking for, right? Okay, and then, okay, stopwatch, digital scale. They give you another row because maybe you could like square the time periods. That could possibly be helpful, right, for this next step. Indicate which quantities could be plotted to produce a linear graph whose slope can be used to determine the spring constant of the spring. So, let's pick up from this one right here. Okay, and there's multiple answers that would work. I want to show you guys at least a couple. Okay, so the poster version of this, probably the most straightforward, or the one you run into first when you start doing algebras. Let's see, I could square both sides. So I could get time period squared is equal to 2 pi quantity squared times m over k. And I'm going to slide the k over here, right? And now look, I have y equals slope times x. Right, guys see that? Right. This is, again, just one way to do this. So you could put time period squared on the vertical axis. You could put the masses on the horizontal, okay? And all these points would line up in a straight line, okay? And the slope of that line would represent 2 pi quantity squared over k. So once you get the slope, you can set it equal to that expression and do a little bit more algebra to solve for that k, okay? Okay, that's what I do. Another way you could do it is, here, I'm going to do it so I can get k exactly as the slope. So I could just cross multiply the k. Let me split this up a little bit. Cross multiply k, and I could get 2 pi quantity squared times the mass is equal to k times t squared. Now this could be my y-axis, this could be my slope, and this could be my x-axis. Whatever. Okay. So what's that gonna look like? Okay. So that could be 2 pi quantity squared times the mass, put t squared down here, okay? And then whatever points you get, again, they're going to line up on a straight line. Okay? But the nice detail about this particular method is that the slope of this is exactly equal to the spring constant. So you don't have to do any additional math. You can just get the slope and that is the answer, okay? Right. And there's other things you could have done too. That's just 2 possibilities. How many guys think you probably got this one right? Probably got this one. Pretty good. All right, you're pretty good, pretty good. Okay, so vertical axis, horizontal axis. Again, like many things you could have put. Could put that set. Could put that set. All right. Briefly describe how the slope of the graph could be analyzed to determine the spring constant. Okay, well, I kind of mentioned that too, right? So if you did t squared versus m, you take the slope and set that equal to 2 pi quantity squared over k, and then do some math and solve for k. Okay? Or if you do 2 pi quantity squared m versus t squared and take that slope, that just is the answer, right? And then you're done. Okay, you don't have to do anything else. Right? Right, guys, good. All right. And then, then I kind of start fresh here. I guess they're just trying to work it up to 12 points. Probably ran out of stuff to ask. I don't know. So, in a different experiment, students attach end of a spring to a force sensor attached to the wall. The other end of spring attached to a cart with mass 0.25 kilograms. That's okay. Well, kind of one of your medium lab masses. The students place motion detector. Oh, look, it's exactly how I told you guys to set the motion detector, how AP would look for it, right? Where see if the cart could head straight towards or away from motion detector. The following graphs show velocity of the cart as a function of time and force versus time. So we got those. Here we go. Here on time. Right. Oh, and look at that. Oh, looks like a sine graph and a cosine type graph, right? Is that? In fact, if you divide by the mass of the cart, or I should say, if you take force and divide by mass, guys, what property does that give you? Acceleration, right? Which would also go hand in hand that, because that would look a lot like this cosine looking graph, right? This consistent, right? Let's see. Oh, if you guys remember what's going on at what point. So where there's zero velocity. Oh, okay. So here's what the cart's doing. The cart's oscillating back and forth. Right? At some points, it's going through the equilibrium where the spring is neither stretched nor compressed. And some points, it's at the end point where the spring might be like maximally stretched and it's turning around. Right? What does zero velocity refer to? Is that where it's turning around? Yep, that would be that it's turning around, right? Hey, if it's turning around at the max stretch point, would that also correspond to the maximum force? And that's exactly how those graphs line up. I say at point zero, that would be the maximum stretch point, wouldn't it? Right. And then with the carts going through the equilibrium point, that should be the maximum speed, but that would also correspond to zero force because it's going through the equilibrium point. And oh, look at that, that lines up too. Right. But that sine and that cosine graph, that's what they'll do. Right. That's what they do. Right. All right. So you guys good with the setup here? About the premise. What are the questions? Part I, using the data from the velocity versus time graph, calculate the change in kinetic energy of the car from 0.5 seconds to 2 seconds. Show your steps and substitutions. So change in kinetic energy, that's delta K. Maybe I should do 1/2 mv final squared minus 1/2 mv initial squared. I could do that, right? Okay, awesome. So let's get some numbers. Got 1/2 0.25 kilograms. I got, okay, we're going from half a second to 2 seconds. So at half a second, that was 0.3 meters per second. 0.3 meters per second. That's being squared. Okay. Then, oh, whoops, no. Sorry, I should have done it the other way around. I'm being silly. Right, so that was zero. That was 0 meters per second. I'm gonna just replace this with 0. Okay. Right, guess that. Because you're going from half second to 2 seconds, I need to start at the 2 second mark, in which case it's 0. Okay. Right, then minus 1/2 0.25 kilograms, and then the initial location was at half a second. That was the 0.3 meters per second. Okay, and then square that. Right. Now this term just goes away. The answer is going to be negative, right? So the final energy is something. The initial energy was 0. So 1/2 times 0.25 times 0.3 being squared. Right. So I'm getting negative 0.01125 joules. You could maybe say approximately negative 11 millijoules. Maybe would work. I think either of those should work. Right. Usually AP is looking for at least 2, maybe 3 digits. So, right, maybe something thereabouts, right? And they don't count off for having the incorrect number of digits, right? Something like that, right? I don't know if they would count off for the negative sign or not. I don't know, right? Right. How many guys think you got that? Something like that? All right, good. All right, you guys are doing good. It's a good sign. Using data from the force versus time graph, estimate the change in momentum of the cart, explain how you arrived at your estimation, and then part III is velocity versus time for the same question, right? The change in momentum. So change in momentum. You guys remember one perspective for change in momentum could be force times time, or if you're in calculus, maybe like the integral of force versus time, right? And then the other perspective for change in momentum could be mass times change in velocity, right? So I think that's the two perspectives we're looking at. Right. So force times time. We're going from ½ second to 2 seconds. So let's check this out. If we're going from, so here's our force versus time graph. We're going from this ½ second here to this 2 second. No. Sorry, 2.5 seconds. Point. There you go. Okay. Ooh, guys, what property of this graph tells you change in momentum? The area. Right? I see a negative area there and a positive area there that exactly zero out. Look at that. Don't they zero out? Right. So therefore, what's the change in momentum equal to? 0. You could say kilogram meter per second or Newton seconds. Right. You guys see that? Right. And then velocity versus time. Okay, see if this says the same answer. So we're going from ½ second there to 2.5 seconds there. Hey, look, it's the same velocity. Right? Both cases, it's the exact same velocity. If it's the same velocity, and you want mass times change in velocity, well, the change in velocity is 0. So that's still going to be 0. Right? Boom. Right. So both say the same thing. Okay. Show of hands. How many guys got 0, 0? You guys get 0, 0? Ooh, all right, all right. Oh man, this is a good sign. Phew. Good sign. You guys are doing good. This one. All right. So just for memory lane, I do remember there was a problem from your college textbook that I sent you guys back in December. I know that was a while back. You guys remember one with like a bear and a basket of goodies? You guys remember that one? Yeah, that's a real classic physics problem. Here it is too. Now, I did last night actually go and design a poster based on this because that really is a classic physics problem. That should have been one of my posters, right? For you guys, the closest thing I gave you guys was this. So you can kind of figure it out from there. Right? But anyway, let's do this one. Right? This one's a little more involved. Right? So got beam, uniform beam, right? So the fact that it's uniform, I can assume that the center of mass of the beam is also its geometric center, which is like right in the middle, right? L/2, right? So you can do that. Right? Actually, this one's a little simpler than your college physics book question because there's no bear and there's no basket of goodies. Right? Okay, so this will be a simplified situation. That's good. Okay, attached to the wall by hinge, right? And then we got the string. Okay, so you guys see everything. It's theta 1. Okay, they just explain in the paragraph exactly what you see in the diagram. Okay, draw and label the forces, not components acting on the beam. So let's do free body diagram on the beam right here. Free body diagram. Well, the first force I'm going to draw is the weight, because if it didn't have weight, then there would nothing. If it was just floating around in space, then no other forces would pop up. So I'm definitely going to put the weight on there. I'm going to put it exactly at the geometric center because the word uniform beam. So let's have this go down. I'm going to draw 4 centimeters. How about that? 4 centimeters, and I'll label it mg, or you can label it f sub g. You have to do one or the other. Okay, right, you guys do that. There's definitely a cable here at the far end pulling at some angle theta up and to the left. Right? So trying to eyeball it and get it pretty close, something like that. Okay. And here, I'll label that F sub T, like a tension force. Right? Now, if I just stopped right there, then would that bar be in equilibrium? No, right? Definitely not, because there'd be a horizontal force. Here are my guiding equations for this. The guiding equations are the sum of forces in the x direction goes to 0, which already that violates, so I know I'm missing something. The sum of forces in the y direction go to 0. This is newtons. And also there's one more condition, which is what? You can't solve this without also knowing torque. Torque goes to 0, and that's Newton meters, right? There you go. There's your, now that's for a 2D plane. If you become an engineer one day, you're going to extend that to 3 dimensions, but this is for 2 dimensions. Okay, like that. Okay. Okay. Yes, which force am I missing? aha, isn't that wall at the hinge point pushing back against the bar, right? But not only that, do you guys think that it's also helping lift it a little bit? Because I do have to satisfy this torque condition, right? So if these were if what I drew was the only supply of the vertical forces, then this would be like wanting to rotate counterclockwise, right? So I'm missing a couple things. Yeah, there has to be a force from the hinge that's pushing back and holding the bar in place, right? Because the wall and the hinge is pushing the beam back in place, right? I'll call that F sub X. And also it's helping hold it up, lift it up. Like if you put your hand there, if you place the hinge with like your hands, like you would be holding it up, sort of, right? That's like an F sub Y. Okay? And if I connect those tip to tail, so F sub Y, right? Then I'll get the actual full force from the hinge. I'll call it F sub H, right? Now, ideally, it's usually a good idea on these for AP to not draw the components. If you dash the components, they usually let it go. But ideally, you just draw those three forces is what we're looking for. Those three forces. Is that okay? Great. That should be the answer. And look, if you got it exactly right, then let's see if all these conditions that I just wrote out here are satisfied. Right, so are they? Okay. Well, do you guys see how I drew it such that the left and the right cancel out? That satisfies this condition. Do you guys see how these two upper components could be like, that could be 2 centimeters, that could be 2 centimeters, this is 4 centimeters. Hey, do you guys see the verticals also sum to 0? That's that condition. Right? And okay, the torque one we're gonna hit in a minute because that's gonna solve the next question they asked. Okay. Now this one happens to be symmetrical. Like, do you guys see how I drew the tension force and the hinge force? They look the same magnitude and also the same angle above the horizontal. You guys see that? Right. I think that should be exactly correct for this particular question. Again, if you throw on the bear in the basket of goodies, that goes out the window and those forces are going to be different. Okay. But with the uniform beam and exactly as they present it, that should be the exact correct answer. Okay. Right, guys got that? So 3 forces: weight, tension force, hinge force. Okay. Got that? All right. That's right. This is the next question. Is they say, well, what if we take that cable and scoot it down there? Then the question is the new tension, let's call this tension 2, is it greater than tension 1, less than tension 1, or the same as tension 1? Right. So the cable used to be here, and now we're going to move it down here. Right. Show of hands. How many guys checked the first box and say the tension went up, the tension increased? Who said that? Yeah, I would have checked that one too. Check how right there. Right. Now here's maybe kind of way to think about it. Right. What if, I mean, you could play around this angle as a variable, couldn't you? Right. This is just my own like rough way of thinking of it to start with. I'll do work with you guys here in a minute too. Right. But what if this was straight vertical? Right. That may be like a boundary condition, extreme condition. You could check out. Right. If that's vertical, I bet the wall hinge is also pulling vertical, and each of these is holding it with half the weight of the beam. So if the beam weighs 100 pounds, I bet this is 50 pounds and 50 pounds, or something like that, right? Okay. And then as you rotate this this way, it's like, okay, well, not only does it still have to hold the same vertical component, but now you're adding on even more horizontal component. And the overall, if you do Pythagorean theorem, this could turn into Pythagorean theorem, couldn't it? Right? The vertical component squared, the horizontal component squared, add them together, square root, gives you the total force. So even though the horizontal components are staying the same, if you're adding more and more, sorry, the vertical components are staying the same, which would be like each of these would be half the weight of the beam. Right? Saw that before. Right? Okay. That's this here. Right? You guys see how if the beam weighs like 100 pounds, this could be 50 pounds up and 50 pounds up, like strictly vertical. Okay. All right. Okay, so justify your answer. Maybe I could, okay. Using a qualitative reasoning. Okay, so that's what I was trying to do, is give you sort of a qualitative answer, maybe something like that, right? I might mention Pythagorean theorem or something like that. Right. Now, part C, starting with Newton's second law of motion in rotational form, derive an expression for the magnitude of the tension in the string. Express your answer in terms of m theta, physical constants is appropriate, right? So I was a little bit confused when I saw Newton's second law of motion rotation form. Thing, isn't that torque equals I times alpha? But this doesn't have any acceleration because it's static. So what is that about? I think what they're really trying to get at is they just want you to use torque and not just forces and geometry, right? Because the full way to do it is going through torque. So I'm going to say the sum of torque goes to 0. That'd be Newton meters. And I think it's really what they're trying to guide you guys towards. Okay, so let's do it. Let's pick. So we're doing on time here. We got till 25. Okay, got about a minute here. Okay. I'm gonna pick this point right here as the pivot point. You guys see this could be the pivot. You see it? And then I got this length crossed with this force, and then this length crossed with this weight, and that should zero out. So I'm gonna go, some torque goes to 0. So at L/2, I've got mg, and that's pulling clockwise. I'll call clockwise negative, just usually do, right? And I'll say plus, and I'll call this one the counterclockwise as positive, right? So the full length, L, I've got the tension force Ft, right, times what, sine or cosine of theta? Here, oh, sorry, here's your theta. That'd be sine, right? You guys see sine, right? Because if this angle was 0 degrees, there'd be no torque at all. Sine of 0 is 0, right? Go back. Right? If this angle was 90 degrees, we pull straight up, you get maximum torque, right? Because sine of 90 degrees is equal to 1. Anyway, this all has to zero out, 0 to 8 meters, right? And now, see, we're trying to solve for this tension force right here. I guess yet, all right? Let's see, I'm gonna cancel the L's. L goes away. And then, what else we got? So mg/2, slide this over, is equal to tension force times sine theta. Right. So the answer should be tension force is equal to mg/2 sine theta. I think that should be the answer. Right. Should be right there. How many guys got that? How many guys got that? You guys got that? That's a little tricky, maybe? All right. Maybe pick up some points. All right, that'll be your pause point. Hope you guys do well on your 7th period exam, and well, I'll see you next time. See you one more time this week.